2 critics, 5 restaurants. One never gives above 3. The other never below 7. They don't share a single score. But line up their picks, best to worst, and the order is the same. Every number different. The ranking, identical. How? Here's the setup. Both critics visit the same restaurants, the same rows of data, but each fills a completely different scorecard. One scores ambience, service, cleanliness. The other, flavor, plating, value. 2 views of one thing. In machine learning, you'd call them 2 modalities. In the lab, 2 assay blocks. Same samples, different measurements. 2 scorecards. Can we boil each critic down to a single number? First, the pieces. Critic A's card is a data matrix, call it XN restaurants across, P criteria down. Critic B's card is Y the same restaurants, different criteria. Now we want one number per critic. So we take a weighted blend of each card, a recipe of weights, and collapse the whole scorecard into a single score. That blended score has a name, the canonical variate. For critic A, it's the card times its weights, X times A. For B, Y times B. One verdict from each, built to be compared. But here's the catch. Critic A is harsh, everything lands between 1 and 3. Critic B is generous, nothing below 7. Their numbers never match. And yet, dish for dish, they rise and fall together. Different scales, the very same shape. One grades low, one grades high, so how can they ever agree? Plot the 2 blended scores against each other. Each dot is one restaurant. Now watch 2 numbers. Correlation asks only whether they rise and fall together, ignoring scale. Covariance is their shared spread scale, and all. Rescale critic A, and stretch the axis. The covariance grows with the stretch, because it's tied to the units, but the correlation doesn't budge. That's the whole idea. Canonical correlation analysis maximizes correlation, not covariance, so it hears the shared pattern and ignores how loud each critic is. In symbols, the cross-covariance term on top, divided by the square root of each critic's own variance. One more complication. Each critic has habits. Critic A always pairs cleanliness with service score 1 high, and the other follows. But that internal link is just a personal tick. It isn't agreement with the other critic. Before we compare, we have to divide it out. What if a critic's scores just reflect a habit? Watch critic A's own criteria. Cleanliness and service move together. A tilted cloud. Whitening straightens that cloud into a circle. It strips out each critic's internal habits, so a shared tick can't masquerade as shared taste. Statisticians call it whitening, or spherring. In machine learning, decorrelation. Do it to both cards, then keep what's left in common. The cross-covariance of the whitened views the matrix K, and its singular value decomposition. But hold on to one catch. Whitening blows up directions, a critic barely varied. Remember that. Picture each cleaned up critic as a point of view, a single direction. If their 2 directions nearly line up, they strongly agree. If they're far apart, they don't. And there isn't just one axis of agreement. Once you've found the strongest, a second, independent one is waiting behind it. How far apart are their 2 points of view? Those 2 directions sit at an angle, and here's the payoff. The canonical correlation is exactly the cosine of that angle. A small angle, cosine near 1, means strong agreement. In symbols, rho equals cosine theta, where theta is a principal angle literally. How far apart the 2 viewpoints sit. To a machine learning ear, it's the cosine similarity of the aligned axes. And they come in a stack. The strongest pair first, then a second pair at right angles to it, an independent axis of agreement, each with its own smaller correlation. Notice what we never did. Pick a winner. Neither critic predicts the other, swap them, and nothing changes. It's symmetric, but there's a trap. Give 2 critics 40 criteria and only 8 restaurants, and they'll agree perfectly by pure luck. So how do you know the agreement is real? So which critic is right? Neither, and 3 honest points tell you why. First, symmetry. Unlike regression, which predicts one thing from another, this treats both views as equal, swap them, and the correlations are unchanged. Second, overfitting, agreeing by luck. To check, shuffle the pairings and see how high the correlation climbs by chance. If your real number isn't clearly above that noise, it isn't real. In high dimensions, regularize, add a small ridge to the diagonal. Third, that catch about whitening. When variables vastly outnumber samples, its cousin PLS, which maximizes covariance instead of correlation, is steadier, the mix-omics and Diablo world. And read the loadings, not the raw weights, when your criteria are correlated. So one menu, every thread, 2 scorecards became 2 matrices. A weighted blend became each critic's single verdict. We measured agreement by correlation, not covariance, so different scales couldn't fool us. We whitened away each critic's habits and found the strongest agreement as the smallest angle between their viewpoints, with independent axes stacked behind it. And we stayed honest about luck. 2 critics who never wrote the same score, ranking the world the same way. That shared order has a number, the canonical correlation. They never used the same words or the same scale, only the same order. And that shared order is the whole of it.